And hi ho there, thanks for coming back for another exciting video. And I'm being sarcastic, or maybe it's exciting. It depends what else you have going on around you. But in any case, free energy, the topic of free energy in chemistry and a chemical change. Yeah, it's a bit elusive, isn't it? Free energy, this G thing, is some kind of representation of the likeliness of a reaction to be spontaneous, not necessarily how fast or how vigorously, but some kind of description of Mother Nature's desire for it to occur. We know if delta G is negative, the reaction wants to go forward, the change wants to happen. And I personify it too much, but that's the way it goes because that's the way I think about it. And if delta G is positive, we know it does not really favor going forward. It probably favors going backwards. If you think about it, every chemical reaction or change being in equilibrium, going forward or backward. Anyway, let's get to it. Do you remember from last semester we described this thing called Hess's law, where if we wanted to know we use the enthalpy, the change in heat, for a particular reaction, we could manipulate a set of other different reactions that we knew the delta H values for, and sum them together, add them up, and in doing so, cancel intermediates and find out that the enthalpy change for the overall reaction was equal to the sum of the enthalpy changes for the individual reactions. Well, if you don't remember that, I think I'll come back to you pretty quickly. So let's say, for example, I'm given in this case 3 reactions. I'm supposed to manipulate this one and this one and this one to get what I call, personally, just me, I call it the target equation. So 3 carbons, 4 hydrogen molecules give C3H8, one of those. So I look, what did I do? What am I going to do? The first reaction. I see C3H8 on the left-hand side, and I see it nowhere else in my given equations. But I eventually want in the target equation to get C3H8 on the right-hand side. So guess what I'm going to do to this first equation? And you can see it down below there, don't you? I flipped it backwards because I want the C3H8 to be on the right-hand side, not the left-hand side. I'm ignoring these other things, hoping they'll cancel. And if you're skillful at choosing your manipulation equations to work with, then they will. All your other junk will cancel. The second equation, I see CO2 on the right-hand side, and oh my gosh, that's gonna. I can't really focus on that. I mean, it could, but it's going to confuse me because I see CO2 here and here, and I don't see it anywhere in my overall equation. I suppose I could guess, let me turn this backwards and multiply by 3 because I wanted to cancel this 3 carbon dioxides. But perhaps I'd rather focus on this carbon. I have 1 carbon here and 3 carbons here. Carbon in this equation is on the left-hand side, just like this carbon, but there are 3 of them here. So I probably want to get 3 carbons here to match these 3 carbons. But in doing so, I must take this times 3 and this times 3 and that times 3. Oh yeah, I forgot to mention, you know what happens to the delta H? I know this isn't delta H, but the same rules apply. What happens to the free energy of a reaction written in the forward direction as you flip it backwards? Yeah, you see it changes sign, doesn't it? And the last equation I am to manipulate, supposedly, allegedly, hopefully. I see H2O, oops, I see no H2O, I hope that cancels. H2 molecule, oh, there's an H2 molecule. H2 molecule here and nowhere else, but I see it here in my target equation, but there's 4 H2 molecules instead of 2, so what do you suppose you're going to have to do to this equation? Well, you see what's going to happen. You see what I've done. I took a times 2. So I take this times 2 to get 4, take this times 2, take this times 2, take that times 2, and hopefully things start canceling out as I rearrange, add my manipulative equations. I don't know what they're called. The equations I'm working with. I add those together, see what cancels. 3 carbon dioxides cancel. 3, 4, 5 oxygens on the left-hand side. Oxygen molecules cancel. 4 water molecules cancel. 4 water molecules cancel. And I just sum up those numbers, and lo and behold, this reaction looks spontaneous. But 23 kilojoules isn't a huge, on the scale of kilojoule numbers, isn't a hugely negative number. The more negative the free energy, the more spontaneous the reaction would like to go forward. Interesting. Alright, let's look that again, and I hope, maybe you'll take the time to pause the video right now and try this. On this one, I've only given you two equations to manipulate, this first one and the second one. Looks like I'm talking hydrogen peroxide, and what's the free energy for this overall reaction? I'm giving you a hint, you got to use those two numbers, but what do you do with them? And that's determined by what you see up here. You're pausing the video now, aren't you? Wink, wink. Jeopardy music, and I was going to say something. What was it? Dang, I have a short memory. Okay. Assuming that these two equations are what we need, I see H2O2 on the right, H2O2 on the right, but I see two H2O2s here and one H2O2 up here. I'm thinking I might have to take this all times 2. Two H2s here, I don't know. O2, I don't know. H2O gas, oh, I see one H2O gas here. I'm sorry, two H2O gaseous molecules and two H2O gaseous molecules. But this is on the left and that's on the right, so I'm thinking I might just want to flip this one backwards. See what I did? That's what I did. And don't forget to manipulate the delta G, the free energies, for that particular reaction as you took this times 2. Did I? Really? Oh yeah, I did, right. H2O2, 2H2O2. Wait, good, yeah. Gosh, I was going to say something insightful and important, but I forgot what it was. What a scatterbrain. Oh, I see I made a mistake there and I corrected it. So what cancels two H2 molecules left and right of the arrow? So whatever's on the left of the arrow and the right of the arrow, just like a system of equations in math, cancels. Oh, get outie. Oh, I see. Oh, tricky. One oxygen molecule here cancels one oxygen molecule here, but not both of them. And oh yeah, and that leaves one oxygen molecule on the left-hand side still uncancelled. And the overall delta G is positive, and I suppose positive delta G means non-spontaneous in the forward direction. So will water and oxygen tend to come together to make hydrogen peroxide all by themselves? No way. That's very largely positive and not likely at all. There's another way to do it, although it seems different, is actually it boils down to the same thing, and it's called products minus reactants. Just like we've done for the delta H values, the enthalpies of formations and the entropies of formation, we can talk about the free energy of formation under standard conditions for all compounds. And these are all tabulated for us in the tables. Appendix 4 in this edition of whatever textbook. I have no idea what this was. It was a long time ago. These are my old notes. I'm going through my old notes, using those as a video lecture series. So here's a very brief listing of a few compounds. The free energies, just like the delta H values, delta H's and delta G's for pure compounds in their, pure elements in their standard states are zeros. So those are zeros, and you might be expected to know that. But if I was going to make carbon dioxide from carbon and oxygen, carbon, coal, solid, and oxygen gas, it would have a free energy formation of this value. Remember, these delta G values of formation aren't really measurable directly, but we can get a handle on them in various other indirect routes. So in other words, if I was forming carbon dioxide from carbon and oxygen, it's this likely to happen. If I was forming water from hydrogen gas and oxygen gas, it's this likely to happen. If I was forming diamond from graphite, it's this likely not to happen. I say not to happen because it's positive. If I was forming hydrogen gas from hydrogen gas, well duh, it's zero because it's already hydrogen gas. If I was forming methane from carbon solid and hydrogen gas, it is this likely to happen. Likely because it's a negative. So these numbers are tabulated for us in tables again. And believe it or not, it's just sort of like it's sort of like Hess's law kind of a thing, to where if I knew the free energy of formation for this and the equation that went with it, if I knew the free energy formation for this and the equation that goes with it, if I knew the free energy of formation for this and the equation that goes with it, and the free energy of formation for this and the equation that goes with it, and this is 0, but I could still write it down if I wanted to. I could add those, manipulate those equations, all those equations together, and get, in a Hess's law type way, the enthalpy of formation, the enthalpy of reaction for this reaction. But it's also the same thing as saying products minus reactants. So I look at the carbon dioxide, and 2 waters, and 4 ozones, O3, and that's not 0 because ozone is not an oxygen in standard state. In any case, yeah, this is a very similar procedure to things we've already seen. Products minus reactants. And that was so much fun. Let me just scroll through a few additional examples. I mean, you know how to do products minus reactants of enthalpies and entropies, and now we're discovering you can do it also with free energies. So you could pause the video here and try this one if you want. Or not, who has the time for that, right? But at some point you got to practice this. So products, and that's the H2O2 here minus reactants here, this one's 0. But interesting, this delta G, this form of solving for the delta G of formation of H2O2 should give us a similar answer than something we did just a little bit ago. But I'm not going to bother to compare it. This is the candy and the chlorate demonstration. I think I did. I have the answer down here somewhere. Theoretically, if I manipulated this and this and this and this and this and all their associated free energy of formations, I could add them together and see some cancellation, just like in Hess's law type question. But it's actually easier just to go products minus reactants. So I go 12 of these and 11 of these and 8 of these minus 8 of those, and also minus 1 of those, and that's an ugly number. What the number is, seriously, did I do this? I swear, I hope I did. It's down here somewhere. There it is. Products minus reactants, as I was saying. Whoa, negative 6647. That's a big number. That's very, well, it's exothermic for one thing, but it's very spontaneous. So the delta H is very negative. And we could say that's what forces delta G to be also probably very negative. But we could do this just based on entropy and enthalpy. So if you see the demonstration, you know it's very exothermic. So the driving force is definitely delta H. Delta H is negative. The delta G value I figured out down below. What was that? Down below. Oh, negative 6647. Okay, that's a lot. That's a big number. So that's it's this number. But and I think it's probably the enthalpy and the entropy. Why would the entropy change in this reaction drive it forward? Primarily because they have a solid here, or honestly a liquid if I melt it, but it doesn't matter. Solids and liquids have more entropy than solids, but gases have a lot more entropy. I'm making 11 moles of gas here and 12 more moles of gas here. Creating more moles of gas definitely makes more entropy, and so the entropy change and the enthalpy change, because it's exothermic, drive it forward, and we found below the delta G to be negative 6647 kilojoules for that reaction as written. That's a big number. I get kind of wound up about this. I have one more example. For this thermite reaction, we could go the products minus reactants for the enthalpies of formation, like you've seen before. And then I could go products minus reactants for the entropies. The standard entropies are not zeros for the pure elements, you might remember, interestingly. And then I could go the delta G equals delta H minus T delta S at room temperature, or honestly it's a little bit, well, whatever. And I get a value. So we've seen that. Or maybe you've seen that. I hope you've seen that. But what we're telling you here with this new video is there's another way to do it. And the other way to do it is simply to look up and compare the free energies of formation of those compounds. This one's 0 and that one's 0 because they're pure elements. But the free energy of forming this from aluminum and oxygen, and the free energy for forming this, the iron and oxide, And so believe it or not, it's the same thing, equates down to basically the same thing or very close to the same thing. And so the free energy, no matter how you slice it, is negative 850-ish. I got negative 842 here by the products minus reactants of the free energies, and I got, what did I get up here? Negative 838. So I got close to the same value. The numbers vary a little bit. Many of them are measured. Different tables, different results. Guys, thanks for watching. That was kind of a longer one than I thought it would be. Take care. See you in class.